In this video, we're going to be building off of some of the concepts that we established in the previous video, namely one-dimensional kinematics and Newton's laws, in order to describe how we can talk about the motion of objects when they undergo rotational motion. So to give you a reminder of some of the things that we talked about in one-dimensional motion, we had these two important equations for one-dimensional kinematics. The first equation told us what the position of an object is as a function of time. And this said that x of t is equal to x naught, the initial position, plus v naught t, the initial velocity times the time, plus 1/2 a sub x times t squared, where a sub x is the acceleration of the object. We also had the equation that told us what the velocity was as a function of time. And this equation told us that v sub x of t is equal to v naught, again the initial velocity, plus at, the acceleration times the time. And so this actually just described how an object would move if it was just going to be moving along in one dimension. So if we had some block like this and this was moving along, we can say like the x-axis. So this is the plus x-axis. This is what this would be describing. Now we'd like to extend these ideas to also talk about how things move when they rotate, or when they're not going in one direction in the sense of going to the x direction, but they're going around some arc. So we could consider some arc of a circle like this that an object is going to go around. And we have some similar equations that we can use to describe that motion. And so the first equation says that theta as a function of time, when theta is the angle represented by this right here. So theta as a function of time is going to be equal to theta naught, the initial angle, plus omega naught times t, where omega is the angular velocity, plus 1/2 alpha times t squared, where alpha is the angular acceleration. We also have an equation for the angular velocity, and so the angular velocity as a function of time is equal to omega naught plus alpha times t. Now, looking at this equation, we see some correspondence between the rotational kinematics equations and the translational kinematics equations. And that's really no accident, because there really is some correspondence between them. And we can actually relate these equations if we say that the angle is similar to the position. The angular velocity, omega, is related to the velocity, and the angular acceleration, alpha, is related to the linear acceleration, a. Now, if we wanted to talk strictly about the motion along the arc of a circle, we have an even stronger correspondence, and that's to say that the distance over which an object moves around the arc of the circle is going to be related to the angle that it moves over times the distance of from the point to the center of the circle, or the radius of r. We could say something similar for the velocity, and so if we wanted to find the tangential velocity, tangential linear velocity over the arc of the circle, we could say that that's going to be equal to the radius times the angular velocity. And finally, we could say something similar for the linear acceleration. So the linear acceleration tangent to the circle is going to be equal to the radius of the circle times the angular acceleration, alpha. So something else that we'd like to bring back from our previous discussions when we're talking about rotational kinematics are Newton's laws. And we've seen over the course of all of these videos that Newton's laws are really fundamental to a lot of the discussions that we have, whether it be discussions about energy or momentum or just Newton's laws by themselves. But Newton's laws also are going to come into play when we talk about rotational kinematics. And so we'd like to remind ourselves of what Newton's first law is to begin with. And so Newton's first law says an object in uniform motion remains in uniform motion unless acted upon by an external force. Now, the important emphasis here is on uniform motion. And so what's meant by uniform motion? Well, uniform motion means that something's going to be moving in some straight line without changing its velocity. And it's not changing where it's going either. So it's going to be just moving in a straight line with some constant velocity. And so something we want to ask ourselves is, if some object is undergoing circular motion, does it have uniform motion? And we realize that it actually doesn't have uniform motion, because if something's going around the arc of a circle, It's always changing the direction of the velocity. A second consideration we should have concerning Newton's laws and rotational motion comes from Newton's second law. So to remind you, Newton's second law says that the sum of the vector forces is equal to the mass times the vector acceleration. And so what we'd like to think about here is what is the direction of the force acting on an object when it undergoes circular motion. So we'll have a demonstration to show exactly how this works. In this example, we see a ball rolling around the inside of a circular wooden track. We notice that in order for it to go around the circle, that it has to have some force pointing in towards the center of the circle. Now, when we think about this, it should make sense that this is the normal force due to the track, because the normal force due to the track is going to be perpendicular to the track, and that's going to be pointed towards the center of the circle. Therefore, we can say the force that's causing this to go around in the circle is the normal force pointing towards the center. We also notice that when we remove a portion of the track, the ball continues to go on unimpeded in the same direction. This is consistent with our expectations from Newton's first and second laws. So from our demonstration, we saw that the direction of the force acting on an object that's undergoing circular motion is going to be pointing towards the center of the circle. Now, we could see that that's also going to be the direction of the acceleration if we consider the fact that from Newton's second law, sum of the force is equal to mass times acceleration. If the force is going to point in a particular direction, the acceleration is going to point in the same direction. But there's actually another way that we can come to the same conclusion, and that's to consider the velocity vectors and the definition of the acceleration when we're looking at something that's undergoing circular motion. And so if I draw some object here that is going to undergo circular motion, we can say that it's going to have some arc of a circle here. If this is going to have some constant velocity, it's going to have some velocity vector at every point going around the circle. That's going to be the same length, roughly, or it should be exactly the same length if I draw this to scale. But we can determine what the direction of the acceleration is going to be here by considering the fact that by definition, the acceleration is going to be equal to the change in velocity divided by the change in time. Now let's consider two of these points and call one the initial point and one the final point. And so if we call this one the initial point and this one the final point, we can construct what the acceleration vector looks like by taking the difference between this final velocity vector and this initial velocity vector. And so really what that's saying is expanding out this delta here. So delta v vector is going to be equal to vf vector minus vi vector. And we have experience with adding and subtracting vectors. We know what this should look like graphically. We take the vector vf and then we subtract the vector vi, and graphically what that means is take the vector vf that we have here and then invert the vector vi and then add that to this one. And so what that looks like here is going to look like this. So this is vf, this is vf vector, this is vi vector, and let's make this actually a little bit longer so it shows exactly what I'm trying to show here. This vector is going to point down a little bit more like that. And so the difference between, or the sum of this vi vector and this minus vi, this vf vector and this minus vi vector is going to be some resultant vector that's going to be pointing like this. Right? And so this is the vector vf minus vi. And if we look at this, that it's going to be somewhere in between here. That vector is going to point like this. And this vector vf minus vi vector divided by delta t is the acceleration vector. And we see, again, that the acceleration vector is going to be pointing towards the center of the circle. Now, the last thing that we'd like to do is to talk about specifically what is the acceleration that is pointing in towards the center of the circle. This is what's called the centripetal acceleration. It takes the form a sub c for centripetal acceleration is going to be equal to the velocity of the object that's moving around the arc of the circle squared divided by the distance from that object to the center of the circle. And so when you're doing problems with Newton's second law, what you'd like to do is you'd like to set up your sum of forces on the left-hand side, and then whatever that sum of forces is going to be equal to the mass times the centripetal acceleration. In this video, we explored the connections between one-dimensional translational motion and one-dimensional rotational motion. We also talked about how Newton's laws could be applied to understanding rotational motion. In the next videos, we're going to be talking about how we can use this newfound knowledge in order to solve various problems. Thanks for watching.